Technology is reshaping the world faster than ever, and artificial intelligence and human evolution contextualizing AI in human history helps you make sense of it. We will focus on what it says about life and species. Stay with me, the best part is near the end. Chapter 3: Evolution of Species. Introduction: Evolution of life adaptation, starting with single-cell multicellular organisms, arrival of humans, tools, alternatives to Darwinian evolution, teleology, acceptation, Lamarckism, mutationism, intelligent design, conclusion. Chapter 4: Human Intelligence. What is human intelligence? Acquisition of knowledge, hearing, audition, sight, vision, taste, gustation, smell, olfaction, touch, tactility, other sensory systems, application of knowledge and skills, extended fluidity in human brain skills, recent extinctions, early extinctions, tools, conclusion. Chapter 5: Origin of Machines. Examples of early machines: wheel, shaduf, inclined plane, pulley, screw, astrolabe, timekeeping machines, windmill, water wheel, heat, electricity, printing machine, nuclear energy, computer, and robots, conclusion. Chapter 6: Machine Intelligence. Classic machines, mechanical feedback, concept of learning, multimodal learning, machine learning, linear regression, decision trees, k-nearest neighbors, artificial neural network, deep neural networks, generative models, conclusion. Chapter 7: Humans in Intelligent Environment, Near Future. Carbon and silicon manufacturing of integrated chips, extrapolation, and human-like intelligence adapting to intelligent machines, super AI, impact of super AI on job market, ethics and super AI, always global, fair and just attribution, honest and trustworthy, value of life, conclusion. Chapter 9: Final words. Index: the authors, under exclusive license to A Press Media, LLC, part of Springer Nature 2024a. Joshi, Artificial Intelligence and Human Evolutions, // org / 978-1-4842-9807-7_11. Introduction: Amit Joshi 1:1. Redmond, Washington, USA. The rapid growth in the field of machine intelligence or artificial intelligence, AI, in recent years is truly mind-boggling and has created an unprecedented level of excitement about the field in the minds of people who are in the know, and the people in the know are increasing exponentially. The notion of AI is not quite novel to most people in the 21st century, as many Hollywood blockbusters such as 2001, A Space Odyssey, Terminator series, Matrix series, to name a few, have already introduced this concept in quite a dramatic manner starting in the mid-20th century. Some movies, or at least parts of them, have painted a bright future where AI is helping humans to achieve more by taking over the repetitive, boring, hazardous tasks and giving them time to focus on the activities that really matter and improve their lives, while others have painted a grim picture where AI has progressed to become a superior and more advanced species in itself and is treating humans with hostility and is taking control of the world and treating humans as slaves. Both the scenarios are interesting or exciting from the perspective of entertainment and have made the respective movies a huge box office success. However, when AI can potentially become a reality, the two implications can lead us toward very different paths, and one of them is definitely not desired. I have been meaning to write a book on the role of artificial intelligence or AI in our lives for a few years now, but narrowing down on the scope that would be apt for a single book kept me thinking and ultimately procrastinating. The emergence of ChatGPT and subsequent rise of interest in the topic, coupled with increasing confusion, even scare, about what AI is and what AI can do and how it is going to affect our day-to-day lives helped me zero in on what precisely I wanted to focus on for this book. One of the crucial differences between human intelligence and AI, at least for now, is that AI is totally and completely under the control of humans. AI cannot function without humans turning the power switch on, and AI cannot reproduce itself. So even if potentially capable of doing more than humans, AI does not have free will as of today. However, the development of AI is not entirely organized or planned. Each new step or breakthrough in technology has come as a result of competition between enterprises that employ researchers and scientists and are fighting for bigger market share and higher stock prices. The next step of unlocking AI would be to let it have the two key capabilities: 1. Turning itself on and off, and 2. Being able to reproduce. If AI can acquire these capabilities in some way, it can potentially realize the ultimate fear that is depicted in the movies. Can we somehow control it so that it never happens? It can be a matter of speculation, but most likely these two options are not on the horizon for the enterprises that control the technology for now, and as such are quite unlikely. In this book we touch upon a lot of technical aspects, but this is not a technical book. It is not meant to be restricted for an audience seeking technical knowledge. It is specifically written for a general audience without any prerequisite background in science or mathematics or computers. A reader who is interested in science, or who is fascinated with the beauty of logic, or is open to learning something new, or is curious about the future, or always likes to ask questions about anything and everything would most certainly appreciate this book. As a matter of fact, the topics in this book should be relevant to all the people on planet Earth in one way or another. Although AI is at the heart of this book, I wanted to state at the very beginning where it all started to provide a context into where we are, how we got here, and where we are headed. I always like to compare this to the operation of bow and arrow. If you want your arrow to reach farther, you need to pull the bowstring further back. In order for us to eavesdrop into the future, we need to start investigating our past first. We start the journey with the origin of life on Earth and then follow the evolution of life forms all the way reaching up to humans. Then, we look at what makes humans the most dominating species on the planet, even more so than what dinosaurs were hundreds of millions of years ago. We then look at what made humans more intelligent and superior to all the other species on Earth. Human intelligence is always the yardstick we use to measure artificial intelligence, and thus after learning about human intelligence, we enter into the era of machines and machine intelligence. We look at the present day with AI knocking on the doors with the potential to change our lives as we know it. We move past the present day into the near future with a case-by-case analysis of the impact that AI can generate on our lives without leaving the realms of reality. The last chapters of the book really dive deeper into the role and impact of AI in the near term on our lives, and then follow the thread to look at a much longer-term future and how we should look at AI to help us get there. Many predictions and theories tend to overestimate and exaggerate capabilities of AI, and it makes them turn into works of fiction very quickly. AI has evolved rather too fast compared with all the other technological inventions in the past, starting with the Industrial Revolution in the 18th century. The scope of changes that took tens or even hundreds of years are likely possible in matter of months and single-digit years with AI, and it definitely makes it much harder to get a realistic perspective on it. However, that is precisely the objective of this book, and I am going to make an honest and down-to-earth attempt to paint the picture of near-term future that is imminent. Being in this field almost my entire life, implementing solutions powered by AI in a multitude of fields ranging from relatively ancient oil and gas industry to present-day consumer needs on a daily basis, to state-of-the-art business intelligence and big data and search engine tech at the bleeding edge of its innovations. I have a deep understanding of what AI can and cannot do. I have seen its evolution from a disparate array of mathematical and computer science-based solutions taking bits and pieces from machine learning to its present-day human-like capabilities in the form of ChatGPT and DALL-E that can converse like a human or draw realistic images from textual descriptions, respectively. Another relatively novel aspect a keen reader would notice throughout the book is that there are very few references despite being on the bleeding-edge topic of human evolution and AI. The only references given are about the current and historical facts. No references are needed for the concepts presented. All the concepts mentioned in the book are evolved from scratch from the first principles or common sense, and there should be no need for any reader to drop this book and look up something online, unless of course they want to dive deeper into a specific topic. I like to take pride in presenting these far-reaching concepts all the way from Darwin's theory of evolution to the rise of machines and human intelligence and its comparison with machine intelligence or AI in a way that makes them accessible to general audience without a single mathematical equation or formula. Most of these concepts, especially the ones around machine learning and AI, are typically shrouded in a complex web of mathematics and computer science lingo, making them super hard for the general audience to understand and appreciate. The effects of these technologies are commonly shown through the magical things they can do in most media such as books, movies, documentaries blurring the boundaries between reality and fiction. Coupling that with the vagueness around these technologies makes it really hard for a non-technical person to truly understand what this technology is, what it can and cannot do. This book should unlock these hidden treasures to everyone and help see, appreciate, and even predict the impact of AI just like any data scientist or researcher working at the high-tech companies would. A big change, probably the biggest change in the history of mankind, based on the pace of it, is poised to come in the near future, and we all should be equally equipped to tackle it together to march toward a better tomorrow. The authors, under exclusive license to A Press Media, LLC, part of Springer Nature 2024a. Joshi Artificial Intelligence and Human Evolutions, // doi. org//978-1-4842-9807-7_22. Origin of Life Amit Joshi 1. Redmond, Washington, USA. The notion of artificial intelligence, AI, or just plain intelligence at its deepest level pertains to life. There are plenty of objects in the universe as small as atoms and molecules all the way up to giant planets, stars, and galaxies, which are active in some form all the time and interact with each other, change forms, merge with each other, and even are born, but they are not necessarily alive or intelligent. As per the current theory of origin of universe, all the objects as well as source of energy came into existence starting with the Big Bang around billion years ago, and since then, all these entities have been at work at every instant of time. Why and how exactly the Big Bang was initiated or what was the universe made up of before the Big Bang is something we don't know and may never know with full confidence. However, if we assume that something made it happen, we can understand, or at least estimate, all the subsequent activities. What is more important is that we can understand the current state of the universe with a lot more detail and confidence. We understand that our Earth is a planet, and it revolves around the Sun along with 7 other planets. We understand how the orbits of each of these planets and their speeds of rotations around themselves and around the Sun are determined by their individual masses and the mutual distances between them and the Sun as well as between each other. We can calculate these metrics based on Newton's law of gravitational force, or even more accurately using Einstein's theory of general relativity and curvature of spacetime. We even understand to some extent how the Sun itself is bound with the center of our galaxy, the Milky Way, and rotates around it, and how the Milky Way galaxy itself interacts with our neighboring galaxy Andromeda, and so on. We can also observe and predict the motions of various asteroids and comets based on their sizes and distances. However, from the perspective of being intelligent, none of these objects really exhibit intelligence. These objects are just following the fundamental laws of physics, and there is nothing new coming out of them. Even though at the very microscopic level, quantum mechanical laws may indicate some random and unpredictable events, at the macro level, none of these objects exhibit any unpredictable behavior or a behavior that would proactively change their actions for achieving some ulterior goals. For example, we don't see planet Mars proactively trying to come close to the Sun by altering its shape in order to get more heat, as it's feeling cold, or we don't see an asteroid changing its direction to avoid a crash with planet Earth, which is bound to terminate the asteroid permanently. This is where we draw a line and separate the living from the non-living, separate intelligent objects from not intelligent objects. In summary, the word intelligence, the way we interpret it at least, is intrinsically linked with the concept of life. Hence, we will start our journey with the notion of life. In this chapter, we will explore what life is and what really separates it from everything else. What is life? What is life? It is one of the quintessential questions in the fields of philosophy as well as science. Even if the very definition of life can be daunting, we are mostly very good at classifying any object as alive or not. For example, we know that rocks are not alive, water is not alive, air is not alive, but dogs are alive, birds are alive, even fish are alive. When it comes to trees, it becomes a little tricky as they don't move around like most other living things, but we still somehow know that they are different from rocks and rivers and are alive as well. So, what is it that separates the life forms from not life forms? The comparison between different versions of philosophical definitions of life can be a topic broad enough to deserve a book in itself. We will rather focus on scientific or logical interpretations of life in this book. One of the most widely accepted explanations of life as worded in various encyclopedias and dictionaries identify life as something that encompasses biological processes and some form of signaling and self-sustenance, capacity of reproduction, energy transformation, and growth. This definition can appear too complex and, as a result, far-fetched even by some loose standards. The idea that is trying to be captured here is a list of parameters that can distinguish the living from the non-living. It seems to be hinting at something like a Venn diagram, one where the explanation is trying to draw overlapping circles to isolate everything that we see around us that is living from what we think that is non-living. Let us consider each of the properties that are listed in the definition one by one and to draw these circles to create the Venn diagram. Let us start from the last property, growth. Growth is characterized by physical increase in volume and mass as well as change in shape. Let us try to apply this concept to various objects we see around us. We obviously know that all living organisms show growth. But what about some non-living organisms, say rocks? We can see that some rocks can grow as they roll with the wind and more soil sticks to them, or as they move with streams of water and merge with other rocks, essentially showing signs of growth. What about ice caps on top of the mountains? They grow each winter with snowfalls. Are these objects living? We don't think so. Thus, if we have growth as the single rule to separate living from non-living, it is not sufficient. So, we need more rules or more circles. Let us start adding more of them to the Venn diagram shown in Figure 2.1. One Venn diagram with one of the parameters from definition of life. Let us take up the second one from the definition, the energy transformation. Once again, we know that all living organisms are capable of consuming some form of energy as required for their life-supporting activities, thereby transforming one form of energy into another. Looking back at rocks and ice caps, we don't see clear indications that rocks and ice caps can proactively transform energy from one form into another by themselves. Thus, we can indeed separate them from living things. But what about some other non-living objects such as rivers? We can see that rivers flow from one point to another. With them, they carry pebbles, soil, and rocks from one point to another. As these objects flow with water, they generate heat by friction. Thus, they exhibit a definitive capacity to convert kinetic energy into heat energy. Along with energy transformation, rivers can grow in size as well each year during rains. Now, are rivers alive then? We still think not. So these two circles, or rules as shown in Figure 2.2, are not quite sufficient to separate living and non-living, and we need to proceed with one more. We can continue with our Venn diagram by adding one more rule from our earlier definition. Two Venn diagram with two parameters from the definition of life. Let us add capacity to reproduce, as shown in Figure 2.3. We are quite certain that all the living organisms, from single-celled ones to complex mammals, can reproduce. But what about rivers? Typically, the concept of reproduction is defined in the context of biology, and therefore, cannot be applied to non-living things directly. However, we can take some literary and philosophical liberty and use a more general and broader definition of reproduction as the ability of an entity to create a new entity that resembles the original entity. With this new interpretation or reproduction, let us revisit rivers which seem to satisfy the earlier two conditions. When a river comes across a hill or some obstacle, it can separate into two or more streams. Each of these smaller streams possesses all the similar properties of the original river, and can be considered as offsprings of the river, essentially proving that rivers can indeed reproduce. Thus, with our broader definition of reproduction, rivers can be considered as living. But are they really? We still think no. We need to proceed with our definition and add more rules or circles to our Venn diagram. 3 Venn diagram with 3 parameters from the definition of life. Now, things start to get more interesting as we start adding more specialized biological concepts to the mix. Self-sustenance by definition states that the entity can sustain itself without needing external help. It can be interpreted in multiple ways, and with most general definition, any living or non-living object can be considered as self-sustaining. For example, rivers can continue to be rivers as long as there is a continuous supply of water at its origin. If the source of water is somehow depleted or evaporated, the river would cease to exist. But similar can be stated in the case of living things also. If a tiger does not get anything to eat for a week, it will perish and will cease to exist. In contrast, a river may exist much longer. Thus, self-sustenance, along with all the previous rules, is still not sufficient to separate living from non-living, as shown in Figure 2.4. So, we continue with our definition to add more rules or circles to see if we can classify river as non-living in the Venn diagram. For Venn diagram with 4 parameters from the definition of life, the next one is the ability to perform some form of signaling, as shown in Figure 2.5. This is an interesting one. In living organisms, the cells can signal to other cells to transmit/receive messages or information. Do we see such signaling in the case of rivers? Not in most situations. On some rare occasions, we may see lightning strike a river from clouds in the sky, potentially transferring some form of electric signal from the clouds to the river. Can that be considered as signaling? The answer to this question is negative. There is an intrinsic assumption of proactively sending a piece of information from the sending party and understanding and reciprocating the signals as they are received by the receiving party as per the definition of signaling. Are clouds really sending any information through lightning here? And even if they are, can rivers understand those signals and reciprocate by sending back a signal to the clouds? Definitely not. Thus, this random occurrence of lightning is certainly not a form of signaling. We can then move rivers outside the center of our Venn diagram that is reserved for living entities. Have we then arrived at a place where we have completely isolated the living from non-living? We will need to consider a few more examples. How about cell phone towers? They are man-made and not natural, but nonetheless they are non-living and they are continuously signaling with hundreds or thousands of devices all the time. Are they living? Certainly not, and it is rather easy to separate them using the earlier rules, as these towers do not show any signs of growth or cannot reproduce. 5 Venn diagram with 5 parameters from the definition of life. At this point, we seem to eliminate most entities that we believe to be non-living. Is our Venn diagram final then? Not quite. Let us move outside of Earth and look at some of the bigger celestial objects. How about planets? Heck, how about our own planet Earth, for example? Let us see how it fits in the Venn diagram. We can consider that Earth to be continuously signaling with the Moon to keep it in the orbit through the power of gravity, and Moon reciprocates by staying in the orbit. Earth can certainly grow in size, the way it has since its formation with our solar system, when it got hit with millions of asteroids and comets, absorbing their mass. Earth is definitely capable of self-sustaining. Earth can also potentially reproduce to create a smaller planet-like object if it gets hit with a really big asteroid that breaks out a small mass from Earth. Some theories already suggest that our current Moon was created in the same way from the Earth already. Also, millions of energy transformations are happening continuously on Earth. Seems like Earth can lie at the center of all the circles along with all the living organisms. So, is Earth a living object? Well, no. Definitely not. This leads us to the final circle in the Venn diagram, as shown in Figure 2.6. Biological processes. A biological process is defined as a series of events or actions that occur in living organisms to achieve a particular result. These processes are essential for the organism to grow, reproduce, maintain homeostasis, a stable internal environment, and respond to their environment. Essentially, biological processes are the ways in which an organism's cells work together to support life. This is the final circle where we come up with something that would eliminate everything in the universe that we think is not living. One might say that this rule involves a circular argument, too, where we are essentially stating that non-living objects are things that do not possess properties of living objects due to the presence of the word biological. However, that is not necessarily true. all the biological processes can be perfectly and completely defined using purely chemical and physical rules and laws with logical statements that apply equally well to living versus non-living objects without explicitly using the notion of life or biology for that matter. In spite of being host to all the living creatures, the Earth itself is primarily made up of rocks and minerals, and water, and does not contain cell structure in itself and does not show the aforementioned biological processes. Hence, Earth as its own object does not satisfy this condition. With this final rule, we arrive at the Venn diagram where we can isolate all the living objects from the non-living ones as shown in the accompanying figure. 6 Final Venn diagram with all 6 parameters. Human-defined life now emerges as the only item at the center overlapped by all the circles. Thus, we have completely isolated the human-defined life forms from all the other entities in the universe. If we look a bit deeper, one can argue that with the last rule in the Venn diagram, do we really need all the other rules? It might appear that this single rule can potentially separate the living from non-living. Then why do we need to include all of them? The answer to this question lies in the distinction between the living and the dead. The dead organisms do possess all the biological processes and cellular structure, at least for some time till all the tissues and cells have disintegrated, but they are not functioning. They are not signaling or moving or are able to reproduce and so on. Thus, we essentially need all the other parameters to distinguish between the living and the dead, but only the first parameter is sufficient to distinguish between the living and the non-living. How did life originate? Now, equipped with the full definition of life and what truly separates the living from the non-living and dead, let us look at the question of how it all started. Did life start on Earth? Or did it come to Earth from some other planet, or asteroid, or a star even? Based on the atmospheric and thermal conditions required for most species on Earth, it is rather difficult to imagine a life form coming to Earth from outer space. But is it truly impossible? As it appears, it is not. The idea of an alien life is not new, and it forms an entire genre of literature in science fiction. But with some recent developments in the field, this idea has been brought close to reality and is not just science fiction anymore. Let us take a closer look at the option of life on Earth originating from outer space. Extremophiles, it is quite clear that all the large species or the species that we can see without needing a microscope cannot survive outside of Earth for longer than a few minutes, if that. The reasons being lack of oxygen, extreme cold, excessive radiation from the sun and or other stars, lack of gravity, etc. All the large species would die within a short time if either of these factors were encountered. When all these factors come together, there is just no realistic chance for survival for these species. However, scientists have found a few types of single-celled organisms on the Earth that can potentially withstand extreme temperature, pressure, or atmospheric conditions, and they are called extremophiles. These microorganisms can survive in places like hydrothermal vents deep inside oceans, where temperatures can rise as high as 120 Celsius or 250 Fahrenheit along with very high pressure. There are also some microorganisms that can sustain extremely cold temperatures such as 25 Celsius or 13 Fahrenheit buried inside of ice. There are some microorganisms that can sustain extreme acidic or alkaline conditions or very high salinity. There also exist some microorganisms that can live entirely in the dark, as well as there are microorganisms that can sustain dangerous radiation such as cosmic rays or X-rays and radiation from radioactive materials. Any of these conditions, even in moderation, would be sufficient to kill the entire human race, let alone other animals. However, These microorganisms can not only survive in such extreme conditions but also can grow and reproduce in such conditions. It is quite encouraging that these microorganisms can survive in these harsh conditions on Earth. But what about outside of Earth? Can they take these capabilities and survive in outer space? Where there is no sunlight, no gravity, and continuous, unhindered cosmic radiation from all the neighboring stars. This cosmic radiation is reduced to only trace amounts on the surface of the Earth due to absorption by Earth's atmosphere and deflection by the Earth's magnetic field. To answer this question, a research team from Japan's Kibo Lab and Japan's Space Exploration Agency, JAXA, conducted an experiment on the International Space Station. Their experiment included multiple different species of bacteria, but specifically, the bacterium of type Deinococcus radiodurans stood out as the most resilient and was able to survive for multiple years in the space outside the International Space Station. When a group of surviving bacteria were examined, they observed that the cells in the outer exposed region had died, and the dead cells created a sort of a protective layer, under which the inner cells were able to survive. This research conclusively proves that there is a definitive possibility that microorganisms can sustain the harshness of outer space for a long time and can still continue to live in a dormant condition. However, from the perspective of finding a possibility that life on Earth could have come from outer space, sustaining this harshness of space is only one part of the equation. The other parts include the ability to sustain the impact when the meteorite or comet carrying these bacteria hits the surface of Earth, and the ability to use the energy from the sun directly or indirectly to grow and reproduce. Specific experiments to see if Deinococcus radiodurans can survive such an impact have not been carried out, and currently, the answer is more of a speculatory nature. Deinococcus radiodurans bacteria need oxygen and the presence of organic compounds to generate energy for growth and reproduction. They do not possess the capability to directly consume solar energy and hence cannot be classified as a completely independent species. However, the emergence of such species provides a path where it is possible for yet another type of species to have evolved on another planet that can take a step further and be able to survive the impact as well as be self-sufficient in consuming energy from sun directly, along with having the ability to stay alive in the space for many years. Even if we agree with this theory of life's origin outside of Earth, the fact still remains that the species that came to Earth from outer space must have originated somewhere else. Maybe a planet in some other star system in our galaxy, or even from another galaxy. But then another question inexorably pops up: how did life originate on that planet? So, until we answer the ultimate question of origin of life from non-living substances, the chain of questions does not really end. Let us now look at the other option where life originated entirely from scratch on Earth. This option is also typically a more favored option. Let us try to explore how it could have happened. Our solar system came into existence around billion years ago, when the Sun was first formed. It took another 100 million years for the other planets to form, completing the solar system. There are many theories that have been proposed to explain the formation of our solar system. They differ in many aspects, but most of them agree that it all started from a giant cloud of gas called the solar nebula. It was quite cold and contained mostly hydrogen along with some heavier elements in minuscule amount. Either on its own or with the help of a perturbation likely from a distant supernova explosion, a portion of gas clumped together to form a seed for the formation of star. Once the mass started to concentrate in the clumped region, the increased gravitational force of that region accelerated its growth, and the region quickly grew to become the most dominant entity in the nebula. With the increase in size and corresponding gravity, the center of the clump started to get warmer, ultimately reaching temperatures high enough, about 100 million degrees Celsius, to start the process of nuclear fusion. Thus, our Sun was first formed. After the Sun's formation, it quickly absorbed all the light gases around it, leaving only heavy elements in the close neighborhood. These heavy elements clumped together over the next 100 million years to form the first 4 planets in the forms of Mercury, Venus, Earth, and Mars. At a distance far enough from the Sun around the current location of Jupiter, the Sun's gravitational pull was not as strong and light gases could still exist. They started clumping together to form the gas giant planets like Jupiter and Saturn. Origin of solar system. Focusing our attention on Earth's formation, the first iteration of Earth primarily consisted of the heavier elements that were left out of the Sun's gravitational force, such as carbon, nitrogen, oxygen, and heavier metals, etc. With the increasing size of the Earth, it started to get its own gravitational force and with that, its own unique identity in the solar system. This period extended for about 400 million years, from billion years ago to billion years ago. This period is called the Hadean period, and the Earth started to cool down after its formation during this period. This period was followed by what is typically called as a period of late heavy bombardment, LHB, period. The LHB period started around billion years ago and lasted for another 300 million years till about billion years ago. During this period, the formation of bigger planets like Jupiter, Saturn, Uranus, and Neptune and their increased gravitational pull created a disturbance in the asteroid belt that was present on the outskirts of the solar system. This disturbance initiated the heavy bombardment from meteorites, comets, and other space debris. Although quite violent, this was an extremely crucial period from the perspective of the origin of life on Earth. These meteorites and comets brought key ingredients to Earth, including water. Due to this continuous bombardment, the Earth's temperature rose again to higher than the boiling point of water, and quite a significant amount of water must have been lost as well. However, whatever remained was sufficient for the formation of life. It is important to note that all the neighboring planets, including Mercury, Venus, and Mars, also encountered a similar bombardment and likely received a similar dose of meteorites and comets during this period. However, due to various factors, such as proximity to the Sun, lower gravity, etc., they lost most of the water and other elements in due course. However, Mars has a very close geological structure to Earth and similar size, and it could have retained water and other elements for a longer time than Mercury and Venus, and there is a reasonable possibility that life could have independently originated there as well. However, we have not found conclusive evidence of it yet. Around the end of the LHB period, or around billion years ago, the Earth started to cool down again. As per National Science Foundation, some of the oldest rocks discovered on the Earth near Hudson Bay in Canada date back to this time. However, we don't have any real evidence of what existed on Earth before this time. There are mixed opinions on exactly when life originated on Earth. Some theories suggest it could have started as early as billion years ago, even before the LHB period itself, while other theories suggest it started during the LHB period or around billion years ago. However, the oldest fossils found so far that can prove the existence of life only date back to the LHB period, and, as a result, there is no realistic way to prove or disprove the other theories. Primordial soup. As per the early discussion on definition of life, in order to prove that life originated on Earth, we need to prove the creation of biological structures capable of displaying functions such as growth, signaling, reproduction, etc. from entirely non-biological substances. There are many theories that attempt to provide mechanisms of how this could have happened. All these theories start with a mixture of primitive organic compounds containing carbon, nitrogen, hydrogen, and oxygen such as methane and ammonia with water and dissolved hydrogen and oxygen, typically called a primordial soup. The word primordial means something that existed since the beginning of everything. In this case, primordial soup means a mixture of all the organic compounds that were available on Earth naturally that led to the creation of life. All the different theories that base the origins of life on Earth on the chemical reactions that naturally happened are referred to as primordial soup theories. One of the most compelling primordial soup theories is called as RNA world hypothesis. As per the RNA world hypothesis theory, the first living microorganisms were entirely based of RNA structures. RNAs are the smallest entities that can perform most biological functions such as signaling, reproduction, growth, etc. A single RNA molecule is the most basic part of living cells and contains a single strand of long chain of atoms arranged as a helical structure. Carbon atoms form the central part of the chain in the RNA molecule along with atoms of hydrogen, oxygen, nitrogen, and phosphorus. The DNA or deoxyribonucleic acid found in most living organisms is a dual-stranded molecule where its single strand is similar to an RNA. DNAs typically have a double helical structure. Most of the living cells that we observe today are based on DNA molecules, while only some viruses contain RNAs. This observation would make it mandatory that DNA molecules should have formed naturally from some chemical reactions. DNA molecules are significantly more complex than RNA molecules, and it is far less likely that DNA molecules can form with random chemical reactions. However, a recent study published in Nature 5 magazine supports the theory that early life that originated on Earth can be entirely based on RNAs. The long chains of atoms in the RNA molecules can be broken down into 4 distinct groups of atoms called adenine, guanine, cytosine, and uracil. DNA molecules share 3 of these groups, with the difference of uracil being replaced with thymine. These compounds are called nitrogen bases or nucleotide bases. Unique properties of RNA molecules include the ability to encode information in the form of sequence of the atoms in the chain and ability to act as a catalyst to initiate biological processes. It has also been shown that RNAs are capable of reproducing and transmitting the information contained in them to the offsprings. About billion years ago, it is believed that environmental conditions on Earth reached a critical stage where all the necessary requirements for inducing the chemical reactions for generation of RNA-type molecules were available. These conditions include 1. Formation of Earth's crust. The reverberations from all the early bombardments of meteorites had settled and the surface of Earth began to solidify, forming what we call the Earth's crust. 2. Moderate temperatures on the surface of Earth. The average temperature on Earth at this time dropped below 100 Celsius, making liquid water possible. It could have been spanning from sub-zero temperatures around poles, but overall, it was conducive for the chemical reactions necessary for origin of life. 3. Formation of liquid water. The moderate temperatures paved the way for the existence of liquid water around this time. The water accumulated during the LHB period was sufficient to create oceans covering over 70% of Earth's surface. 4. Presence of complex organic compounds. Earth contained significant amounts of carbon, hydrogen, nitrogen, and oxygen, along with trace amounts of sulfur and phosphorus. 5. And last, but not least, the dense atmosphere on the Earth was able to cause heavy lightning. Such lightning strikes were able to trigger chemical reactions with the complex organic compounds producing RNA-type molecules. The Miller-Urey experiment provided crucial evidence for this process. In 1953, two professors at the University of Chicago, Stanley Miller and Harold Urey, conducted this experiment. The experimental setup was quite simple. They brought two complex organic compounds, methane and ammonia, along with water and hydrogen gas, and sealed them together in a flask. It has been shown that such compounds can be easily produced when the underlying elements are exposed to UV radiation. Then they connected a pair of electrodes to the flask and applied electric sparks repeatedly. Over just a few hours of operation, it was observed that multiple amino acid molecules were formed in the flask. These amino acid molecules are the building blocks for the nucleotide bases that ultimately form the RNA and DNA molecules. To further advance this concept, Thomas Carell from Ludwig Maximilian University 6 based in Germany has recently demonstrated a sequence of chemical processes that conceptually can make not just the amino acids but all the 4 nucleotide bases that are the building blocks of an RNA, adenine, uracil, cytosine, and guanine, from basic ingredients such as water and nitrogen under atmospheric conditions readily available on Earth around 1 billion years ago. With these raw ingredients for the construction of RNA available, over the next several thousand or million years, they were grouped together to form the first RNA molecule. There are some other theories that propose life originated deep underwater. Specifically, near the underground vents at the bottom of the oceans there lies an interesting mix of ingredients such as high temperature to initiate chemical reactions, presence of necessary elements through the fumes coming out of the vents, and liquid water. Even if sunlight is not present at such depths under the ocean, the heat coming from the vents is sufficient to provide the necessary energy for life to survive and grow. The idea is that RNA-type molecules were first produced around these vents, and over thousands to millions of years, they kept combining to form microorganisms with cellular structures. Some of the earliest organisms known to man do come from underwater, and this fact favors this theory of origin of life. However, there is not enough experimental backing for this theory similar to the one provided by the Miller-Urey experiment or Carell's experiment for the theory of origin of life on the land. There are some other theories that claim life could have originated under deep sheets of ice, or inside clay or soil, etc. But most of these theories lack sufficient experimental backing and are not favored by many scientists. Ultimately, last, but not least, the discussion on origin of life is never complete unless we consider the involvement of some superior power such as God. When one claims that the life on Earth or in the universe was created by God, there are not many arguments that can be made against it if we go in the direction of faith. However, we can certainly ask some probing questions if we take this statement in the spirit of logic. If God or the superior entity did create the life, why did it create from the small microorganisms? Why did it not create humans or Homo sapiens directly? Why did it have to go through the long process of evolution? If God created life on Earth, what else did God create? Why was life created only on planet Earth and not on any other planets in the solar system? If God created life on Earth, God must have created the solar system also, and extending the argument, the entire universe as well. If God created the entire universe, Why did she wait for billions of years to create the earth and life after creation of the universe? There is simply no limit to what questions we can ask, and there is no good answer to those other than God wanted to do it that way. So, if God wanted to do all these things in a certain way, in a certain sequence, in a way that follows well-defined laws of physics and chemistry, then we can still try to study our understanding of these laws, improve the equations based on the evidence we see, and be able to predict how we came here and where we will go next. Thus, either way, if God created us or not, we still need to do our due diligence and learn about the universe, learn about our solar system, learn about the Earth, and find out how it all started. Conclusion: life, as we all know it, indeed differs from other concepts in the universe. However, its objective definition may not be obvious, as we saw in this chapter. We take life for granted as we see so many different life forms around us, including us, but at the start, it was far from obvious. It was rather one of the unlikeliest things to happen, statistically speaking. However, it was not impossible, and happen it did. Is the primordial soup the true answer? Maybe, maybe not. But definitely some chemical reactions happened using atoms and molecules that were readily available on Earth that led to the formation of the first biological structure. In the next chapter, we will look at how life progressed through time. The authors, under exclusive license to A Press Media, LLC, part of Springer Nature 2024a. Joshi Artificial Intelligence and Human Evolutions, // org//978-1-4842-9807-7_33. Evolution of Species. Amit Joshi 1:1. Redmond, Washington, USA. Introduction. Our perception of intelligence is tightly integrated with life and living organisms. In the previous chapter, we looked at various processes that led to the origin of life on Earth in the form of single-celled organisms. Routine cellular operations do not show much in the form of intelligence. It is only when we start looking at the actions of complex multicellular organisms such as animals and birds and even aquatic species that intelligent behavior starts to surface. It is not just a coincidence, and intelligence is indeed deeply rooted in the biological structure of the species that exhibit it. Hence, in order to fully appreciate the concept of intelligence, we need to learn about these organisms and how they came into existence. In this chapter, we will dive deeper into the topic of life and look at how the life that originated on the Earth culminated into the creation of complex species such as humans containing trillions of cells. Evolution of life. The first organisms that were created on Earth were primitive single-celled organisms based on a single RNA or DNA and were capable of carrying out all the fundamental life processes. However, the species that we see around us today, including us, are far more complex and contain not just hundreds or thousands, but billions and trillions or even quadrillion cells, where the same fundamental life processes exhibited by the single-celled organisms are now handled by dedicated organs that contain super-specialized cells. Transformation of the primitive single-celled organisms into these highly advanced species did not happen in a short time, or by accident. It took billions of years to reach this level of complexity. There is sufficient archaeological proof that the process that was responsible for it is evolution. The theory of evolution by natural selection is credited to Charles Darwin. Darwin was one of the greatest scientific minds that is known to us. Darwin proposed his theory of biological evolution in the year 1859 AD in his coveted book on the origin of species. theory of evolution is one of the most elegant and groundbreaking theories ever proposed in the history of science, let alone biology. Although it is based on assumptions that are simple enough for an elementary grade student to understand and appreciate, a repetitive chained application of those principles is capable of explaining births of the complex web of all the species that have ever lived on the face of Earth, starting from single-celled organisms. Being fundamentally simple is a quintessential litmus test for many great theories. When a theory is simple, it can either be easily refuted or is nearly impossible to refute. There is little left for interpretation. There is no obscurity in it. There is no vagueness caused by a long and complex chain of deductive arguments. When a theory gets complex, there are typically numerous cases to consider, and although they can be hard to prove, they are also hard to disprove. In the worst case, a complex theory can hide behind its vagueness, till enough research proves all the cases, or in the best case, the theory becomes limited in accessibility only to people that are capable of understanding the full complexity of it. A classic example of such complex theory is string theory, or its generalization in the form of superstring theory, or M-theory. Also, when a theory gets more complicated, the scope in which it is applicable starts to reduce. In other words, theories that are simple in nature are rather broadly applicable, while complex theories try to explain some very specific scenarios with significantly narrower scope. Having said that, it takes a genius to propose or develop a theory as simple as evolution and be valid and capable of changing our understanding of life on Earth. Sometimes, a theory in concept can be relatively, pun intended, simple, but its formal definition can be mind-bogglingly complex. An example being Einstein's general theory of relativity that tries to generalize the Newtonian physics, especially the concept of gravity. It defines gravity not as a force like Newton did, but as a curvature in the spacetime fabric. Thinking of curvature in spacetime is not too hard to understand, especially when it is dialed down to 2 dimensions. A simple 2-dimensional graphic of a checkerboard-type surface getting distorted when a large object appears on it, as one can see in Wikipedia and many other sources, is a great example. However, to understand the full mathematical formulation of it, using tensor calculus, earning a PhD becomes only a starting point. It is also important to note that the real differentiations in visible implications of general theory of relativity compared to Newtonian physics only come into the picture when we go beyond Earth, and even our solar system, and look at stars and black holes that are light years away, or we need to look at some minuscule quirks in the orbits of planets that only a handful of telescopes on Earth can measure. Newton's theory of gravity and motion, which can now be looked upon as a simplified version or a special case of the general theory of relativity, can answer most questions in real life. As hard as it may be to believe, all the sophisticated architectures and engineering marvels on Earth over the last 3 to 4 centuries are built using Newton's laws and not general theory of relativity. Crystal Palace, built in 1851 in London, was one of the first largest constructions at the time built making exhaustive use of Newton's laws. It was constructed using glass and iron structure to make it strong but light, and it was an absolutely incredible engineering feat at the time. The success of Newton's laws just kept climbing up and up, with breathtaking constructions of the Eiffel Tower in Paris, the Brooklyn Bridge in New York, USA, all the way to the Burj Khalifa in the United Arab Emirates, which is the tallest building on Earth by a significant margin, about 200 meters or 600 feet taller than the runner-up, to name a few. Even the design of the gigantic architecture of Burj Khalifa did not need help from general theory of relativity. Newton's laws were accurate enough. This is not to discredit the greatness of general theory of relativity in any way, which truly marks the epitome of modern-day physics, mathematics, and astronomy in the 20th century. But it does illustrate a key aspect of scientific theories that complexity of solution tends to follow the complexity of the problem. The theory of evolution is possibly even simpler to understand than Newton's theory of motion and gravity and needs no complex augmentation whatsoever to make it more general, as yet. This is a work of pure genius. In order to move forward with the specific details of human evolution, let us quickly go over to the fundamental principles of Darwin's theory of evolution. Darwin's theory of evolution is based on two steps that take place in a repeated fashion generation after generation in the life cycle of the species. 1. Random genetic variation in offsprings by the process of mutation during reproduction. 2. Natural selection dictated by survival of the fittest. Let us look at the first aspect of the theory. Every time a species reproduces, an offspring is generated by mixing the genes of the parents with some degree of random variation. If such slight random variation did not exist, then the offsprings would exhibit exactly the same traits as their parents, and no new features would ever be generated. At the same time, if the offsprings are generated using excessive random variations, the continuity of the species would be lost and whole new species would be created in every generation. Thus, there needs to be a delicate balance between randomness and predictable identical replication. These random variations can also be looked upon as errors or accidents in the creation of offsprings when ideally there should not be any variation. With such carefully balanced randomness or accidents, each reproduction leads to generation of slightly different offsprings. The variations in the genetic structure can happen due to mutations, genetic recombination, or even environmental factors. Mutations are essentially the innate errors or accidents in DNA replication as mentioned earlier and can be caused by environmental factors such as exposure to radiation or some harmful chemicals or due to a viral infection. Mutations are commonly observed when cell division happens through the process of meiosis. Genetic recombination is another process by which new combinations of DNA sequences can be created. During meiosis, the chromosomes or DNA sequences in a cell are shuffled, and new combinations of genes are created. This can also lead to new variations in the population. The continuous mutations across all species make the habitat a vibrant and dynamic place where mutual interactions between species are changing continuously. This dynamic habitat sets the stage for the second step in the process of evolution, natural selection. The newly formed offsprings then interact with the environment with three possible outcomes. The new features produced as a result of the mutation make them better at surviving the environment, or they make them worse at surviving the environment, or they don't really make any measurable difference. The third case essentially is a scratch and makes no real impact. In the second case, statistically speaking, such offsprings tend to die sooner with less chance of reproducing and passing those inferior features to their next generations. The offsprings with features that make them better suitable at surviving the environment tend to live longer, especially in contrast with the species with inferior features, giving them a higher chance of reproducing and preserving those new features through generations. It should be noted that these changes cannot be clearly perceived on an individual basis. They should be looked at from the context of large sample space across the entire habitat and through the lens of statistics. Over hundreds or thousands of generations, a definitive drift toward the features that make the species better at surviving the environment becomes apparent. It is also important to note that the environment as such should stay fairly consistent in order to see this effect. When the environment itself starts to change rapidly, it may not give enough chance for the species to evolve in any specific direction to sustain the changes and may lead to mass extinction. However, when the changes in the environment are slow enough, the slow drift toward new and improved features leads to a generation of a whole new species over time that are better suited to the changing conditions. Rapidly changing environment, even when it is not completely devastating, can still make the process of evolution ineffective by resetting it too often. It is important to note that there is always a race for survival among different types of species, and each of them is evolving simultaneously. As a result, the whole process is quite dynamic, but there is an inherent and delicate balance. However, eventually the statistics tend to favor one species over another, and that species evolves into becoming a dominating one. A great example of such a phenomenon was the emergence of dinosaurs. Their eating habits ranged from carnivores to herbivores, and their sizes ranged from measly 2 to 3 inches to nearly 100 feet. However, they all had one thing in common. They all were so much better at surviving in their respective environments that history saw an almost unhindered growth of them across the planet. However, one day, in a fell swoop, they were completely eradicated from Earth with a catastrophic calamity, and it showed that even the most evolved species can perish to natural disasters when their impact changes the environment too fast. During this catastrophic event, although dinosaurs perished, some smaller animals and plants did survive and were able to get on a brand new evolution train once again with the newly formed environment and ultimately culminating in the emergence of humans. Adaptation. The concept of adaptation describes a process of change by which a species becomes better suited to its environment. Adaptation is quite intricately linked with the process of natural selection, and hence evolution in general, but they are fundamentally different processes. Evolution takes multiple generations, ranging from hundreds to thousands, to create new species by altering the genetic structure that is better suited to the given environment as discussed earlier. The rate of incremental change through each generation depends on many factors such as rate of mutation, size of population, and the environment itself. While adaptation is a change in an organism without changing the genetic makeup to help it better survive the environment, adaptation shows its effect on single or few organisms and can happen at a much faster rate, while evolution changes the entire population. Here are some of the examples that are generally given to illustrate the process of adaptation. Evolution of polar bears with white-colored fur to better hide in snow, or webbed feet of ducks to make them better swimmers, sharp teeth of carnivores, large beaks of birds, whiskers, claws, and the list goes on and on. It is important to note that not all of these adaptations have happened in a few generations, as some of them took over hundreds of thousands of years and likely over corresponding number of generations. As a matter of fact, an implicit rule that an organism cannot adapt to its environment in a single generation is at the very heart of Darwinian theory of evolution. If that could happen, then the need to change the genetic information in the form of mutations can become optional. The organism is born with a fixed set of features and is bound to react with the environment with the help of those features alone. There is nothing that can be changed. The only change that can happen is when the organism reproduces and mutation kicks in. However, the changes are only seen in the offspring. If an organism could adapt after birth, the process of natural selection needs a whole new interpretation. Typically, all the adaptations that are observed can be classified into two types. 1. Physical adaptations. 2. Behavioral adaptations. Physical adaptations describe the changes in the body of the organism. The changes like development of wings, webbed feet, sharp claws, capability of running faster, changes in height/weight, capability of breathing underwater, etc. are all examples of physical adaptations. Obviously, it takes thousands of years to see these physical changes, and in some cases, they lead to the creation of a whole new species, thereby merging with the process of evolution. Behavioral adaptations describe the changes in the behavior of the organisms, like hunting in a group, living in a colony, courtships for finding mates, etc. It is important to note that even if behavioral adaptations don't necessarily need changes in physical appearance, they are not seen to happen in a single generation. Even if these adaptations don't need any changes into the physical properties of the species, they are related to the structure and functioning of the brain and nervous system, and the organisms are born with a pre-programmed brain to show these behaviors. These behaviors also do not change with the changes in environment automatically. Starting with single-cell, the principles of random variation of features in offspring during reproduction and natural selection, coupled with adaptation in the Darwin-esque theory of evolution, do provide an architecture that can explain the occurrence of modern humans starting from single-celled organisms about 4 billion years ago, but it does not provide direct explanation of everything that has happened with life in the last 4 billion years. The earliest life forms that appeared on Earth constituted what we call prokaryotes. Prokaryotes are single-celled organisms that do not contain any structural components inside them, such as nucleus or mitochondria. These structural elements inside the cell are called organelles, resembling little organs responsible for specific functions inside the cell. There were two types of prokaryotic species called bacteria and archaea. It has been concluded that in the early formative years of Earth around 4 billion years ago, the atmosphere of Earth was vastly different from its current state. It was much thinner with less density, and it contained very little oxygen, if at all. Nitrogen, carbon dioxide, and water vapor were primary ingredients. As a result, these prokaryotes had to obtain energy using anaerobic processes by using chemicals available in the surrounding environment. Such prokaryotes are named chemoautotrophs. As such, chemoautotrophs did not need sunlight as well and could survive in harsh conditions. One of these bacteria or archaea was likely what scientists call LUCA, or last universal common ancestor, from whom all current life has originated. With the appearance of these prokaryotes, Darwin-esque theory started to come into action. With each successive reproduction of these organisms, some variation of the original species started to appear and the offspring started showing some new features and behaviors. With natural selection trimming the species that were ill-suited to the environmental conditions, the process kept on going for millions of years. About 500 million years into it, around billion years ago, the first cyanobacteria appeared on Earth. They still belonged to prokaryotes, but possessed an entirely new feature with them that enabled them to capture solar energy for their survival. Also, the process of capturing solar energy converted atmospheric carbon dioxide into pure oxygen as a byproduct. As there was an abundance of carbon dioxide in the atmosphere, these species thrived and grew in epic proportions. Their growth had a profound impact on Earth. Their incessant consumption of carbon dioxide reduced its percentage from the atmosphere, reducing its greenhouse effect. As a result, the Earth started to cool down. It not only introduced oxygen into the atmosphere, but also increased its amount to the levels that enabled other species to use it for their energy production. The next major step in evolution was the appearance of eukaryotes. Eukaryotes are also single-celled organisms, but they have a significantly more advanced cell structure that comprises organelles or structural components such as nucleus that contains DNA, mitochondria, or chloroplasts, etc. that have their own membranes. The evolution of eukaryotes from prokaryotes took about billion years and is an extremely complex and fascinating topic that is still a part of active study among scientists. There are a number of different theories describing how eukaryotes could have evolved. The most widely accepted theory is called the endosymbiotic theory. The endosymbiotic theory suggests that eukaryotes evolved when multiple prokaryotic organisms physically merged into each other, forming a single entity. It has been observed that some prokaryotes have a tendency to form symbiotic relationships with each other. In this symbiotic relationship, two organisms live close together and benefit from each other. In the case of eukaryotes, it is thought that one prokaryotic cell got engulfed into another prokaryotic cell. The engulfed cell was not digested or dissolved, but instead lived inside the host cell, continuing to function, and ultimately got converted into an organelle of the host species. There is a lot of evidence to support the endosymbiotic theory. For example, consider mitochondria and chloroplasts, two of the most common organelles found in eukaryotic cells. Not only are they similar in size and shape to other independent prokaryotic species, namely, alpha-proteobacteria and cyanobacteria, respectively, but also have their own DNA. This DNA is similar between them and is separate from the DNA in the nucleus of the host species. Even today we see many examples of plants and animals where such symbiotic relationship is observed between prokaryotes and eukaryotes. The bacteria provide their hosts with nutrients, and in return, they are protected from predators. The evolution of eukaryotes is a crucial landmark in the history of life on Earth. They exemplified a more complex cellular architecture and paved the way for the formation of multicellular organisms. Natural selection further allowed eukaryotes to become more successful than prokaryotes, and they eventually became the dominant form of life on Earth. Multicellular organisms based on the dating of fossils, eukaryotes are considered to have evolved and prospered around 2 billion years ago. The jump from eukaryotes to multicellular organisms is yet another important milestone in the evolution of species. However, definitive evidence of multicellular organisms has not been found until about 600 million years ago. This leaves a huge gap of anywhere from billion years to billion years, when the Earth was occupied by only single-celled eukaryotes and prokaryotes. However, it must be noted that absence of fossils does not make the appearance of multicellular organisms prior to 600 million years impossible. This is another area of active research, and with every new discovery or new analysis of fossils found earlier is changing the currently established timeline of various species. So, these numbers are to be taken as rough estimates only. Even if these timelines can be approximate, the scientist community has a good understanding of how the transition to multicellular species must have happened. At the heart of this is the same symbiotic relationship that led to the formation of eukaryotes from prokaryotes. The process is likely much simpler than what was thought earlier, and it is highly likely that it has happened not once but multiple times in the history of Earth. An example of chlamydomonas is typically studied to explain this transition, as it represents one of the latest transitions that happened just about 200 million years ago. Chlamydomonas is a simple eukaryotic organism that has a cell wall, a nucleus, and chloroplasts. It reproduces by dividing in half. As a first step in the evolution of chlamydomonas, they started to form colonies. The colonies as such were still a group of many single-celled organisms. Over many thousand years, the different cells in the colonies started to take up different and specialized functions based on their location in the colony. Some cells became better at feeding the entire colony, while some other cells focused on reproduction and subsequent growth of the colony. With such specializations, the colony was no longer just a group of cells, but it now had a complex and well-defined structure. These specializations also helped the colony live longer and grow faster than the other colonies that were not going through these changes. Natural selection helped prioritize these colonies over time. After continued changes toward more specialized functions, cells lost their individuality as well as ability to survive on their own, ultimately leading to the formation of a true single multicellular organism called a sponge. Arrival of humans after the birth of the first multicellular organism, the subsequent changes are much more streamlined and took place at a relatively breathtaking pace. To give a comparison, it took more than 1 billion years for the first single-celled prokaryotes to evolve into more sophisticated but still single-celled eukaryotes, while it took less than 400 million years for first multicellular species like sponge to evolve into first rat-like mammals known as Morganucodon. Mammals are an extremely complex and sophisticated species that exhibit advanced features like presence of hair or fur on the body for protection from the environment, being able to produce milk to feed their offsprings, along with advanced body structure comprising specialized jaws, backbone, and spine, along with an oxygen circulation system powered by a heart. Then the evolution of mammals like Morganucodon to primates in the form of Purgatorius or Archicebus took less than 150 million years. The primates mark yet another big milestone in the chain of evolution with even more advanced features such as forward-facing eyes giving binocular vision, hands with ability to grasp with fingers, larger brain, improved vocal tracts and communication abilities, and so on. The evolution from early primates to first hominin in the form of Sahelanthropus cadensis took less than 60 million years. From first hominins to first of the Homo species, Homo habilis, took less than 5 million years. And from Homo habilis to Homo sapiens, or modern humans, took only million years. The evolution of the present generation of modern humans, or Homo sapiens, dates back to about 200,000 years with origins located in Africa. There is some debate among scientists around the precise timing, and some believe that Homo sapiens appeared on the face of Earth as early as 300,000 years. It is well understood that the Homo sapiens coexisted as well as interbred with other related species such as Denisovans and Neanderthals for a certain duration of time, but ultimately eradicated the other species altogether. The differences between them were relatively minor, mainly pertaining to cognitive abilities. To give quantitative rationale, the similarities in the DNA between Homo sapiens and Neanderthals is about %, while between Homo sapiens and Denisovans is about %. To compare that with other species, Homo sapiens share 98% of their DNA with chimpanzees while only 97% with Homo erectus, making us genetically closer to chimpanzees than Homo erectus. In order for species to interbreed, the DNA needs to be extremely close, typically over 99%. Most modern humans carry about 2% DNA from Neanderthals, while people in Melanesia too inherit about 4% to 6% of their DNA from Denisovans. Since then, humans have migrated all over the Earth and now have occupied almost all the habitable land across the entire planet. This spread is quite phenomenal and absolutely unprecedented in the history of life on Earth. No other species has been able to occupy the regions on Earth with so much diversity in climatic conditions, without spending hundreds of generations of evolution in those regions. Genetic scientists have found evolution of some minor but new traits being developed in humans living in different regions of Earth, but nothing close to the creation of a new species. Over the last 100,000 years or so, the physical appearance of humans has not changed much. However, behavioral changes have certainly happened on multiple levels and at unprecedented speed, and they certainly don't follow the notion or rate of behavioral adaptation as seen in other animals. Let us consider an example to illustrate the differences. If you pick a large enough group of lions, about a few hundred or so, from tropical forests and put them in the Antarctic region, most likely the whole group will perish in a matter of a few years if not less. In a similar manner, if you pick a similar group of polar bears from Antarctica and put them in Amazon forests, they will likely perish just like the lions in a matter of a few years if not less. The same can be said for most other animals, except for some microorganisms, as they are already adapted to survive in harsher conditions. Most larger species just cannot cope with the sudden changes in the environment or habitat of this magnitude and perish. On the other hand, consider a situation where we pick a similar group of humans from Amazon forests and put them in the Arctic region, or vice versa. We also make sure that the group is not connected with the rest of the world in any way and cannot get help from there. Within their lifetime, the group of humans will start creating weather-appropriate clothes, footwear, will build a new type of housing appropriate for the new climate, will create new weapons to hunt the animals in that region, will figure out plants and vegetables that they can use as food in that region, and ultimately will survive and even grow in population. They will likely not be happy at first, at least in the first generation, but nonetheless they will not perish. Tools. This brings us to the concept of tools. This seemingly simple and casual example actually has rather far-reaching implications from the perspective of evolution. This example paves a way toward the fundamental shift away from Darwinian evolution. As a matter of fact, if humans don't need to evolve to adapt to the changing environment order of magnitude faster, there is no need left for their evolution. The main driving force toward evolution is adaptation and survival of the fittest species, but humans have created something entirely game-changing so that they can adapt and survive in any climatic condition that the planet has to offer while staying biologically and genetically as is. The secret sauce that helps humans achieve this incredible feat is the invention of tools. The very notion of tools is quite generic and vague, so let us bring some clarity to it. Tools can include anything that humans have created using their natural organs, hands, feet, brain, etc., and leveraging living or non-living things available on Earth. Typical examples would include clothes, weapons, houses, automobiles, and even pets. The role of humans in creating pet dogs from wild wolves is well researched and documented. The creation and use of tools marks probably the greatest achievement by humans, that puts them in a completely different league of species. No other species has shown the ability to create such tools with the agility that humans exhibit. There are examples of other species also using tools, like chimpanzees using sticks to pick up insects, or using leaves to drink water from streams, etc. However, there has not been any changes in these tools over hundreds of thousands of years. Same can be said about birds that build nests, bees that build honeycombs, etc. However, the ability to create and/or use these tools by these species is attributed to evolution, that took hundreds of generations to materialize, and not adaptation, that can happen in a single to a handful of lifetimes. Tools make humans independent from the need to alter their physical appearance. These tools augment humans' core appearance and capabilities and adapt them to survive in the changed environment. The advanced brain of humans is also capable of changing behavior in a matter of days or even hours. We are capable of learning from past experience and can work in groups when needed or work alone when that is more effective, can communicate with each other to pass on the learnings in a matter of minutes and not generations, and so on. In other words, we can adapt in the same generation to such an advanced level that other animals need hundreds, if not thousands, of generations to achieve. It should be noted that all the tools we have in the 21st century were not available over 300,000 years ago when humans first came into existence. It took a long time for us to get there. Although from the biological sense, humans were not quite evolving during that time, but the tools were. Alternatives to Darwinian evolution. So far, we have discussed the evolution of species from the perspective of Darwin's theory of evolution based on genetic variation and natural selection. Although this is one of the most widely accepted theories, there are some alternate theories that have been proposed. It would be interesting to investigate some of the top contenders among them. If a theory is foolproof, there is no scope for scientific alternatives to it. For example, we can consider Newton's laws of motion. All the three laws have been proved beyond doubt by repeated real-life experiments and observations of natural phenomena, unless we go to interstellar distances and speeds close to that of light. And as such there is no scope for any alternate theory to explain the physical interactions between objects. Even if Darwin's theory is so elegant and brutally simple, it is based on a sequence of logical arguments coupled with varied randomness over billions of years, unlike Newton's laws that are entirely based on mathematical equations with no scope for any randomness. As such, it is not hard to poke holes in the theory of evolution. In spite of it being in such a delicate situation from the perspective of experimental proof, there have not been any fundamental flaws that have been discovered in it. Still, there are some challenges that cannot be completely ignored. Here are some of the main criticisms. 1. Inability to explain origin of life. 2. Inadequacy in explaining inconsistent fossil records. 3. Difficulty in explaining apparent teleology or evolution with purpose. And 4. Difficulty in explaining adaptation versus exaptation. Darwin's theory really kicks in after life has already originated, and as such the two underlying principles that drive the theory cannot explain how life came into existence in the first place. We looked at this in great detail in the earlier chapter, but none of the theories were based on evolution. This criticism is fair, but it simply points out the bounds on the phenomena that can be explained with evolution and does not really. That is the heart of artificial intelligence and human evolution, contextualizing AI in human history. If it helped, a quick subscribe keeps more summaries coming. So how do life and species connect? That is exactly where we started. Go back to the top and watch it click into place.